to start in a few minutes, but I thought I'd just ask you guys, how many people here have used Openstack?
3.
Who knows the difference between Apple Swift and Openstack Swift?
What's
Okay, well, sure, touch on that.
Oh, yeah, I know what that is.
Okay.
What is Apple Swift?
It's the language for like doing.
Well, I know that there's
All the recruiters want is you have to have like 5 years.
Right.
Yeah, if you've been doing it for 3 weeks, you're a senior developer.
Objective-C out of the market.
Oh, that's right. There you go.
Takes the objective out of C.
It's the new
Mobile approach, yeah, the mobile platform.
Is it just for mobile, but how about desktop too?
Yeah.
Just for Mac.
Mac.
Yeah. It's all the same Cocoa API framework, so right? Yeah.
All right, let's rock.
That's a really good question, by the way. Because that's what people say, C is Swift. This is,
All right, so this is the last talk of the day. Don't forget the speaker forms in the back to fill out, and then we're going to have some drinks and a raffle. Yay! So let me just introduce Adrian Otto from Rackspace, who's going to talk about Apple's new Swift programming language. So I'm just kidding. So it's going to be about Openstack. So please help me welcome Adrian.
Thank you. So, for those of you who like to take pictures of the slides that have like all the pie charts on them, don't need to take the picture because at the end there'll be a QR code that you can scan and download the slides. And I will have some of those slides. I work at Rackspace, been there since 2007. My role there is principal architect. I also do standards work on Oasis. Camp is a cloud standard that we're working on. I'm also the project technical lead for an OpenStack community project called Solar, which is about making cloud technology more accessible for developers. And I'm also the chair of the OpenStack containers team, which is focused on making containers a first-class service within OpenStack hubs. So I'm the kind of guy who is happy all the time. I wake up every morning with a smile on my face to go to work. And the reason why I'm so happy is because I get to do essentially whatever I want. And so what I choose to do is focus on next-gen technologies. So all about what's going to make things easier, faster, cheaper, better. So that current focus for me is finding a way for these things to work together better. So polling all of you, how many of you know what OpenStack is? So OpenStack is a cloud technology. It's open source. It allows you to run your own cloud. It provides resources that are programmable through API interfaces. It has compute, storage, networking, orchestration, telemetry. I can go on and on. Well, new ones are there's a data platform now. There's hosted databases, queues, whatnot. Solon is in that ecosystem as well. Docker, again, a show of hands for Docker. Okay, Docker is much newer, which I'm not surprised there are fewer hands. Docker is very recent. It was founded in 2013. It is a technology that makes Linux containers easier to use and introduces a bundling technique for making container images that are portable between any system that runs a Linux kernel. So you can bundle up an application and move it from machine to machine and it's still runnable. It's a very interesting technology. It has a layering concept. So you can create essentially what amounts to a snapshot and make a change and make another snapshot. And if you say, start my application, if you've already started it with the previous snapshot, you're only going to transfer the delta of data across the network in order to start them. So they start much more quickly. Also in 2013, Rackspace acquired ZeroVM, which is a next generation virtualization technology. It is not a hypervisor. So if you're trying to mentally put this into a category, like Zen, any kind of VMware product, KVM, it is not a hypervisor like that. It is a process level isolation that runs directly on top of the host that allows you to turn things backwards. So normally when you use virtualization, you are in the process of moving your data to your application. And your application stays in one place, generally one instance. This is the opposite of that. It's about having your data be all over the place and moving your application to where the data is. So you need to think of it as exactly backwards from the same way that you think about using virtualization. Virtualization, super popular, everybody's using it. Why are they using it? Because they've got lots of applications that don't use up a whole machine, and it gives them the ability to pack all that on the less hardware. Openstack clouds, fewer people using these, it's newer. But this is a way to get on-demand resources through a programmable API. And there are both public and private options here. So you can use the open source software, you can use that in your own environment. You can use a public cloud like Rackspace that uses an OpenStack, uses OpenStack software, and there's a compatibility that you can expect between them. So containers, when I talked about the portability of containers are particularly interesting because it allows you to prepare your application one time and use it whether you're running it on a virtual machine, whether you're running it locally on your laptop, whether you're running it on bare metal, it doesn't matter. It's the same application. So all these things are super exciting. This is what I spend my day thinking about. And the reason why all of these things are interesting is because they're allowing us to move faster. Everything is about getting it faster, getting it on demand, getting it now, getting to value sooner. So for those who, I lived through a software development paradigm when we used a method called waterfall. Waterfall kind of lends itself to a selection of trade-offs. And so we have this triangle that kind of describes, you pick two of these things, right? You can get cheap fast and cheap slow. You get the idea. Today, we don't develop software the same way. We develop it using more of an agile approach, and we iterate in very small iterations. We try to use continuous integration, continuous deployment, and software is much more about fast, fast, fast than it is about taking trade-offs. And the reason why this is important is because if I give you enough fast, you don't need cheap anymore because you're getting value sooner. And if we're doing iterative development, you don't need good necessarily because you're iterating gradually towards that good. Okay? So life today is all about fast. So, which is the fastest? What, if we're all about getting fast, what's going to give you the most fast? So if my goal is start a virtual machine on an OpenStack cloud, how long should I wait to expect from the time that I give the order until the time that thing is running? So the best case is going to be around 2 minutes, maybe 2 or 3 minutes is typical for using performance flavors on Rackspace Cloud with a default image, and you're not doing a whole lot after the node comes up. 2 minutes is typical. If you've got a custom image and it's enormous, and you're doing all kinds of stuff, chef recipes and crazy setups and all kinds of things happening after the boot, of course, sometimes are a lot longer. Bring in Docker. Docker kind of changes this so that you're getting to runtime for an update to your application in a few seconds rather than waiting minutes for boots. So we've made kind of an order of magnitude shift from what we thought was fast with virtualization in cloud now is getting much, much faster with containers. 5 milliseconds, or 5 seconds sounds like something that's really fast, unless, well, I'm going to stop and tell a story. Now, I know I'm between you and beer, so this will be a short story. But in the Solon project, we're in the process of implementing CI/CD. So we take code from a Git repository, we build it, we produce a container image, that container image gets put on the cloud. Okay, super hard. The container build process, if it worked on using a virtual machine builder, would take 5-10 minutes in order to run the CI. That's typical. So we don't want developers to be waiting 5 or 10 minutes in order to get to, my code is tested and I know it's green and it's solid and I can iterate again. You don't want developers stopping to sip coffee, you want them applying their knowledge and creating value. So we use Docker for the build process instead, and used a technique where we can cache the prior set of data, and now we can do builds in a few seconds, where before it would only take a few minutes. So now we're doing this order of magnitude improvement in speed, and we're getting developer productivity as the product of that. The ZeroVM takes this a few more orders of magnitude. So now, if what I'm doing is a data science problem, and I'll get to how ZeroVM works and what the use cases are in a minute, but if I can do this in milliseconds now instead of seconds, I've broken through to a whole nother territory. So let's talk about ZeroVM. This is my nutshell set. Okay. Processing in ZeroVM is single-threaded. There is no concurrency. There's no network, because you're operating on local resources. Technically speaking, I'll get to how you actually interact with the network, but there's no Ethernet interface, for example. You don't talk TCP/IP out of a ZeroVM container. And there's no access to the file system. Okay? So your whole world about how you think about writing applications does not apply to ZeroVM. It's not reading a file, reading configuration out of a file, doing things over the network with TCP/IP, none of that. It's totally different. Okay? There are 6 principles that the project is based on. Small, light, and fast. It's got to be functional. It's totally open source licensed. Very secure, which I'll talk about in some depth. Very scalable and embeddable. So the scalable one is important because things need to be scaling in proportion to the number of additional nodes I add. So if I have performance X and I double my number of nodes, my performance should be 2X. That's the expected behavior. So Adrian is telling me there's all these restrictions and I need to think about stuff differently and everything is backwards, but what is the same? The thing that's the same is when you do build these applications for ZeroVM, you use the C99 API, which is a subset of POSIX. Okay, so if you understand POSIX, minus a couple of things, like the ones I outlined, right? Access to networks, right? Sockets are local, and of course your file system, you don't have any file system like that. You write to that API and you can compile it as C code, right? Using a GCC toolchain. Or you write Python code. And the Python runs natively on the bare metal, on the host where the application is dispatched to. And I'll get to why that's interesting. Because it's single-threaded, you get deterministic behavior. This is important. When we run software today, that we have a lot of stuff going on all over the place, the CPU in the systems executing that code determines the scheduling of what threads run and when they run. So they don't necessarily run exactly the same way each time you execute it, depending on what's happening on that system. In ZeroVM, you get the same output every single time. Guaranteed. There's no difference in the output depending on what's going on in the machine. I get the processor, I'm locked to the processor, same inputs, same outputs every time. Determinism is extremely important when you're doing data science. Let's talk about how I/O works. Okay. Does anybody remember web programming with something called the CGI interface? CGI, in other words, Common Gateway Interface, yeah, old guys. It's kind of like that. Okay, it's super dumb, simple like that. The standard in file handle is your input. Your log goes to standard error, and standard out is your output. And that's it. If you want more I/O, you can define more I/O. You can put a ZeroVM queue. You can use ZeroMQ ZBroker in order to do a named network pipe and get data into or out of a queue as well. But most ZeroVM applications are going to be doing I/O just using these 3 standard priorities. What runs is very restricted. So the memory is access restricted for security reasons. The read and write, the total amount of bytes read and written by that application are defined in advance. When you create the virtual machine, you tell it how much data you want to allow it to use. And there's a set lifetime. So you set how long this thing should live, and when that time is up, it's up. So here's what the architecture looks like. The thing that's most interesting here is that the part that you bring is this pink stuff. This is your code. And around that is a set of trusted code. And a whole bunch of techniques for how we actually virtualize what we run, and how we protect your code from interacting with anything else that might be happening on that host. So the reason why this is interesting is that I can run any code in there. I don't care. I can assume that that code is hostile. So as a public service provider, I can stand up a service and allow customers to give me arbitrary code that I'm running with other virtual machines that belong to other people running their untrusted code side by side on the same host, and not worry about these things interfering with each other by performance or by security. The syscalls that you have access to are also limited now. I wanted to talk about all of the restrictions. I'm going to skip this in the interest of time. If you are interested in exactly how we limit within ZeroVM, you're welcome to look at the slides. I have more resources as well. This is what the memory stack looks like. One thing that's interesting about this is that the manifest, the user manifest that describes this application is included in the actual executable, which is, in addition to this, it's got a read-only stack. So why all this? Why all this restrictions? It's all about making sure that it's secure. It's about having confidence that somebody is not going to break out of that container, get control of the kernel, and once they've done that, they own everything that's on that box. It's about giving you a sense of security against that risk. So, Openstack Swift, not to be confused with the new Apple programming language, is a code name for the project called OpenStack Object Storage, or OpenStack Storage. This is a horizontally scalable storage system. It has a RESTful API, so in order to put an object in, you use a REST operation for a foot. To get something out, you do a get in order to read it. It's 2 levels, so it's not a hierarchy like a file system. You can create containers and you can create entities within those. So you can think of that as like there are directories, 1 level of them, and then in each directory you can create files. You create as many containers as you want, you can create as many files as you want, but they just don't mess. So this is a system that scales horizontally to effectively unlimited amount of storage. Rackspace today runs a many petabyte scale installation. Storage in a system like this is very inexpensive, on the order of about $500,000 per petabyte. It can run on just about any hardware. And as you accumulate data in a system like this, I want you to recognize that data, like mass, has inertia. The more of it you have, the more difficult it is to move. And if your technique for analyzing your data requires you to move it, then it will make your problem harder and slower the more data you accumulate. So if there's a network between where you do your processing and where your data lives, then that network's got to become infinitely fast and infinitely cheap in order to keep up with having an infinite amount of data. So how do we deal with this, right? Well, I told you before, we're all about speed, speed, speed. How do I get this to go fast, fast, faster? Well, in order to make t time lower, I've got to make rate bigger, right? That's it. I've got to either have fewer bytes or I've got to have bigger rate. So why don't I just join like the compute and the storage and run them together, and then I can get a much bigger rate, and then by not moving it over the network, and that would be fantastic. The problem is service providers can't really do this because applications require lots of CPUs and memory, and storage systems require lots and lots of storage. And if every storage node look like a monster with a gazillion CPUs and a goddamn huge amount of memory and more hard drives than you've ever seen, well, then cloud computing wouldn't be affordable. So this doesn't work. Can't do this. What you can do is you can allow people to run arbitrary code on the storage system in a safe way. And that's what ZeroVM is trying to enable. So Zero Cloud is the combination of OpenStack storage and ZeroVM. The way that it works is in the proxy nodes, there are two kinds of nodes in Swift cluster. There's a proxy node, which is what hosts the API that services your requests, and there's the data nodes, which actually hosts the physical data. ZeroVM goes on every single node in the cluster, which gives two ZeroVM node types. The types that can do mappings and the types that can do reducings. For all of those of you who understand the MapReduce paradigm, this will come naturally. So the Zero Cloud architecture simply sits on top of the Swift, OpenStack Swift architecture. And it has a job manager that will accept the request. The request is actually a bundled application. So it's not a query. It's the application, it's the code itself. So it takes the code, makes it into a job, puts it through a connector. It ends up on an executor. An executor creates a session, which then performs whatever the action is, can produce the outputs. The outputs can go back into a thing called the reader. The reader can decide to store the stuff in the storage system or return it back to the user. This is how it works. So that's nice. What are we going to do with this thing? So there are a few killer apps. When I first heard about ZeroVM, I heard this long list of things that it might be able to do. And the list is like 25 things long. And once somebody tells you like 25 things, 25 killer apps you could potentially do with this, your mind starts to go like, because you can only hold like 6 or 7 things in your working memory at any time, right? So I'm going to give you 3. First is video transcoding. So imagine that the reason why you're using cloud storage is because you're archiving unstructured data in very large blobs. So if I'm doing video surveillance, and I'm putting the video surveillance data into a cloud, and I'm not expecting to want to do any analysis on that until I have a good reason to. And then suddenly I might want to do analysis on that. I might want to write a Python function that would look for how often people move, or where they move, or answer some really good question about what's happening inside those videos. My Hadoop cluster is not going to help me answer that question. But a ZeroVM application potentially could. Here's another one. My video is in the archive. It's in some raw, super high def format, and I want to be able to stream out of my storage system and put it into a very compressed format to play on a mobile device. But I don't want to store it in my storage system twice. I just want to store it in my storage system once, and since I've got tons of idle CPU in my storage system, use that CPU to just transcode on the fly, particularly if I have a lot of long-tail content. So content, particularly rich content, is only interesting for a very short period of time. After that, it becomes much less interesting. What video was recorded 4 years ago is not particularly interesting, and having that in 44 formats is also not particularly interesting. It's a big waste of my resources. I would like to store that once and have the ability to pull it out in any format I want. Computable object store. Anybody worried that they might be watched? Who might be watching? What they are watching, I don't know. But wouldn't it be nice if your data were actually stored encrypted? Today, if you want to do this, you encrypt the data before you put it in the storage system. Or the storage system has the key in order to read and produce more data. If the key is there with the encrypted data, how valuable is the encryption?
It's not very good.
It's not valuable at all. It's Pointless. Okay, so my storage system sees that data as opaque. I can't act on it now. So I've got to take and read that encrypted data out, decrypt it, hold it somewhere, act on it, and then if I want to store it back, after I've maybe changed something, I've got to re-encrypt it and send it back. Well, what if, instead, I do that, but after I've saved it, I want to tell the storage system, do something on my data, and by the way, here's a temporary key that will work to read the data that you will only have for the duration of this operation, after which it's destroyed. Now, I can have encrypted data that I can actually read under certain circumstances. And the exposure of where the key is much more limited than having it on every node in my entire storage cluster. MapReduce. I'm going to skip this. Everybody knows what everybody in this room probably knows what MapReduce is and why it's interesting. Yeah?
Well, how do you guarantee that the key is only useful for a certain period of time, or that it can't be stored or something?
That would depend entirely on what encryption scheme you use.
Oh, okay.
So it's theoretical.
Oh, okay.
So you can use key splitting, you can use time-based key splitting. There's all kinds of techniques for how you get that done.
Okay.
But this is an enabling technology that would allow you to act on encrypted data at rest without moving it. You use the CLI on a Linux box to grep for something. It takes a long time. Why does it take so long? Because all the data's got to string through the grepper in order to find it. Now, what if the thing I wanted to grep was really, really big? Well, then it would take a really, really long time in order to get it through some pipe. But using a ZeroVM system, right, remember the 2 layers, right? I've got potentially thousands of storage nodes, and all of them are working on a subset of the data at a time. This kind of in action, which seems totally insane, that you would try to do a grep through that much data, starts to become possible. So now you can think of the other 21 killer apps what you can do with this. And to do all of those things, so I'll talk a little bit about usage and then I'll talk about how you actually do it. So this is how the thing works. There's a little tool called ZPM, it's a command line utility. You write your code, you bundle it using ZPM bundle, and then you do a ZPM deploy. This is the name of a Swift container. Containers like a directory. And then you give it this ZAP file. The ZAP file is a YAML description of your application. In this case, it's a Python application called sysinfo, and it's going to give your output to standard out. So basically, you're going to run this, and it's going to tell you something about the node that's running this. So I'm going to get the number of outputs is the number of nodes that I have. This sysinfo.zap file would be whatever, Adrian's app.zap, and would be different if I wanted to do a MapReduce style. It would be different depending on how I want my my input and output interfaces to be defined, how long I want things to run. So there's a lot more in here. I've put a little tiny dot, 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 and there's a bunch more stuff that fits in here. This is the general idea. So once you've deployed it, then you can execute it, and you'll get the output right away. So if you want to try out this Zero Cloud, there is an environment called Zebra. Zebra is hosted by Rackspace. It's a ZeroVM running on top of the Swift cluster. It's currently in early preview, so you request access to it. Within a couple months, it'll be generally available. So if you want to try it out, this is all hosted, so you can just not worry about setting up an Openstack Cloud or Swift or configuring anything. It's all set to go. This is the URL where to find it. And this is where you find me on either Freenode or Twitter, and where the slides are this time. Thank you all. Questions? Yes.
So a little deeper on ZVM, is it completely different than C groups and LXC and all that?
Yes, it is totally different.
And it appears to the host OS as a process executing user space?
Yes.
Or, okay.
Exactly.
But the performance guarantee stuff, you don't need direct kernel access.
If you wanted to do performance sharing, you could actually combine C groups and ZeroVMs. So if you say, I want this ZeroVM to only get 25% of the CPU available on this box, you can do that. You can put them in combination. They are compatible.
So, in general then, or as far as the implementation, so you're kind of assuming that for your object store, you've got these x86-based systems, and generally, they're generally resource constrained because they weren't designed for compute. And ZeroVM is going to allow these restricted applications to, everything is restricted, I/O, memory, whatever. You can only get and access on, and can only act on against one particular object, or could it act against?
No, that's defined here in the ZAP file.
Okay.
So this one's saying, oh, this one doesn't have it. Okay. Well, this is where you define what it is. So
Okay.
you say, I want it to act on start.text. Okay, and so like every text file in that container is going to be active on. Or you can give it other patterns. You can have it be parameterized if you want. So it's flexible in that way. So no, it doesn't limit you to only acting on a single object, but it's acting on a single container.
Okay.
Yeah. At least with Zero Cloud, it acts on a single container.
Depending on the implementation. Well, then that kind of blows my whole idea, because what if the other object is somewhere else? What happened?
Well, you're going to have a container, and you're going to have gazillions of objects that are spread all over the cluster.
So if you called multiple objects, you'd have multiple instances of the same
Yes.
ZeroVM job.
Exactly.
And
So back to that diagram.
the system figures that out.
Exactly. Just like if you're using a Hadoop system, right?
Ah.
Your name nodes can give you clues to where to find the data in certain ranges, right? You're going to use an algorithm to determine where the data is. It works the same way here. The data is hashed out in the cluster. So you run the algorithm, it knows where to run the ZeroVMs based on where your data is and what it knows about the predicates and the how you define the work.
That could be a lot of fun.
Yeah.
The 3D.
QR code back.
Yeah, I'll give it, sorry. Yeah, sorry about that. More questions? All right, so we are exactly on time. It is 6 o'clock. My understanding is they're here.
Yeah.
In the cafeteria.
In the cafeteria. Thank you, everyone.
Same here, network.
Networking.
Networking runs on beer.
Beer?
What's beer?
Huh?
Yeah, good to see you. See you over there. A lot of stuff, man.
Yeah, this is sort of exciting.
Yeah.
Get the rounds. You're gonna get some beer over there.
Yeah, see you.
Just require.
I know we give like a generic service first, and then we can specialize to get actually hosting a generic environment.
So, thank you. What, just a real quick question. Great job, Avery. Where are you located?
I'm here in LA. We're Donna Beach.
So I run a meetup group called Media Entertainment Design.
Really?
I guess I should go to that. It's Mustache LA.
They might like this talk.
They might, that's why I'm hanging out here.
Okay.
So this would be really fun. So I'll just reach out to you through the slide.
Yeah, it's adrian.otto@rackspace.com. It's my email.
All right. Good. Good. Thank you very much.
Yeah, I'd
Sorry to interrupt.
love to come talk to your folks about it.
Media entertainment?
It's so meetup.com/mess-LA for Los Angeles. And there's a Bay Area one.
Good meeting you.
Okay, thank you.
a specialized hypervisor where the guests are Java virtual machines. So all of the ones that have like, all of the J runtimes, it makes more sense to run on top of that. And I think that's called, I'm not blanking on this right now, XVM, I think it's called. So that would make more sense. And that way you'd have access to the full language runtime and it wouldn't be as restricted. Because the restrictions are going to be different based on the way that the language behaves. So trying to make it work with Scala and Java and all of those doesn't make a lot of sense, but it would if it's something that can be compiled out in a C code. Or an NACL binary. I didn't mention in this talk because I kind of skipped over the deep implementation stuff. That's the native client, the Chromium native client. It's a Google thing for running native code running native x86 code that you generate with C++ that runs natively in the browser. So you can run arbitrary code in the browser on the host with certain restrictions wrapped around it. And that's how Chromium OS is implemented. Or Chrome OS, right? Chromebooks, all of their apps, all those apps run in NACL.
Interesting.
So it's the same technology that was the leverage in ZeroVM. It's the same restrictions. So anything that can be compiled to NACL can also be run on ZeroVM.
We've been talking about a problem domain for dealing with the growth of video and video storage on premises and off premises. I think there's some kind of business out in there somewhere that we're trying to hone in on. Because Openstack does a lot of processing and then storage really well. And dealing with Stefani as a filmmaker, software engineer, but we've become all too familiar with raw storage and the challenges there. I had a meeting on Friday, Thursday, with my old boss who is getting involved with sports. He's talking about using some kind of system. I'm starting to think of that. You take this card out of the system, and then, you can do a lot of have an app do the video editing on your phone. Is this something that's I'd like to maybe pick your brain about this in terms of it being something that's up and also down. Are you guys doing your work to scale down?
NACL is a perfect example of scale all the way down. Right? All the way down to a single browser that runs on a extremely limited hardware device. Right? So you can run the same code in ZeroVM running on a embedded device that you can run remotely. If you want to run the same thing kind of as a cloud app versus a local app, or you can run parts of it locally and parts of it remotely. Like access to the video stream and acting upon it might all be remote. But handling the user inputs and everything might be local. Or you might do working on some buffer of the video locally and then working on the entirety of it. Like when you publish a video, you like to convert it to a whole bunch of different formats. So you might do like all of the upfront transcoding in cloud, whereas you do the native format, the rich format once on a local device.
Well, a big problem with like people that take